All right, very good morning. Welcome. This is the first ISTEC distinguished lecture for the fall semester of 2019. For those of you who are not familiar with ISTEC, the Information Science and Technology Center here at CSU. ISTEC has activities of all kinds that focus on things of interest to information sciences and technologies. We hold research fora, we have workshops, we hold the whole Future Vision Conference every couple of years, and probably one of the most popular events we hold is this Distinguished Lecture Series. And today we have a very distinguished lecturer to come and give us a talk, but to introduce him, let me get on the stage. Rocky Law from Electrical Engineering.
So it's our great pleasure to have Professor Roy Yates come here. Roy obtained his PhD from MIT. He's currently a distinguished professor at Rutgers University. Roy is a well-known expert in communication network area. He is the author of the textbook we use in our undergraduate probability course, EC 303. And Roy has initiated several important research topics in the communication network area, including energy harvesting, wireless systems, and the age of information. And today he will talk about age of information with us. And let's welcome Roy.
I think it's working. It's a pleasure to be here. The way the scheduling works, I teach in New Jersey tomorrow, so I was forced to spend the weekend here in Colorado, and it was a very charming weekend. We're all very, very lucky to live here, so share that. So this talk, it's kind of a long title, so it's good to kind of deconstruct. First thing you see is this notion of status updates, and status updates are everywhere. They're part of our everyday life, whether it's Facebook or Twitter or Reddit. Status updates are something you see. This talk is about status updates, but it's not about any of these status updates. These kind of social network updates, the delays in communicating these updates maybe. Is there a microphone problem? Is it? Yes? And the problem is it echo, or should I just yell? If I turn it. Okay, maybe. Is that better? So if I turn my head, it stops working. This is challenging, right? But like I like to, maybe I'll just look at my slides. Okay, so I'll stand here and kind of, I'm very skilled at just yelling at people, right? I lecture to 200 undergraduates and I just scream at them, and they're all pretty happy without a microphone. In any case, these sorts of updates, if you receive them a minute later or 10 minutes later, generally those things are fine, and if the network takes 100 milliseconds or 1,000 milliseconds to deliver these updates, that's insignificant compared to the time scale in which you listen to them, and in fact, so we're not particularly interested. So what we're really interested in is this idea of real-time systems where you have network devices and applications that interact with us in our environment, and they have to do so quickly. So the kinds of things we're thinking about here are like vehicular safety messaging. At various levels, people are proposing that automobiles make a lot of measurements, and they exchange those measurements. They could be as simple as like vehicular status, position, velocity, acceleration. They could be more complicated messages like, here's an image that I'd like someone in the cloud to analyze this image. But in fact, all of these messages should be exchanged quickly. Another kind of example would be real-time remote access, things like remote surgery. So on the left, there's a surgeon who operates a hand controls at a console, and she may be in one city, and the surgical theater may be somewhere else, and she is sending messages to this robotic surgical tool to execute the procedure. Virtual reality is another example of involving status update messages. The virtual reality player moves about locally, and that has to generate new images in her headset, and those things have to be done quickly. A third example is augmented reality. You take an image of something and you send some metadata, and somebody in the cloud augments the image. Like these kinds of, this sort of simple version of the picture maybe doesn't require very fast response, but you can imagine using this in ways that responses have to be faster. So all of these examples can be kind of put into kind of a canonical model. And the canonical model is that a source sends updates to a monitor. So you can think in the vehicular setting that the red car is producing these updates, and they go through some kind of a network or a service facility. And maybe the monitor is some entity in the cloud, but also maybe the monitor is just the blue car that's nearby. And there's kind of a thing we use here, kind of that we'll see throughout the talk, that will denote updates by these little triangles, and an up triangle signals an update that's generated and put into the network. And over here, a down triangle is an update that's delivered at some other time to a monitor entity. So in the case of the robotic surgeon, the updates are the surgeon's hand motions on these controls, and the monitor is the robotic surgical tool that receives these updates as commands and then performs the surgery. In the case of virtual reality, the updates are the head movements of this VR player, and they're received by some monitor who's then responsible for generating an image, a reality, a virtual reality for that person. So the monitor in this case is the cloud server. In this example, when you think about these systems, I've been working in this area for a while, and I spend a lot of time going to talks and thinking, well, is there some kind of an update hiding in this system, right? So you think about the different ways of formulating how this system works as updates. And for instance, in this case of virtual reality, maybe a better way, and a useful way sometimes, is to think of the update as kind of as part of a round trip process, right? The player adjusted her head, repositioned her body. That message goes to the cloud server, and the cloud server responds with the new image, and you treat the image that arrives in the headset as the update. So you think of the VR player as both the source and really the true monitor, because it's the player who needs to see the new image. Depending on what you're doing, this is a useful way to think about it. So all of these systems have kind of required kind of response times, and I'm being a little vague about what I mean by a response time, but roughly it's how long it takes for an update message to reach some kind of a monitor. In vehicular settings, people talk about 1 millisecond kind of response times. The same thing goes for kind of mission critical IoT messages, which are like machine-to-machine communications, maybe in some process control application. Virtual and augmented reality, particularly virtual reality, you would like these updates to be delivered within 10 milliseconds of the person moving their head. And then there are a variety of other applications, various things in the cloud. Mobile gaming is a good example where 10 to 100 milliseconds can can be acceptable. So typically these things are the result of kind of physical requirements of the applications. So in the case of like vehicular updating, the way to think about it is that a vehicle moving 36 kilometers per hour, which is kind of a speed you would move in downtown Fort Collins, corresponds to moving 1 centimeter per millisecond. And 1 millisecond of delay in delivering an update means that the car will have moved 1 millisecond. I'm sorry, 1 centimeter. So a second example would be in virtual reality. Like if you move your head and the updated image takes more than 10 milliseconds to show up, people start to feel queasy. It makes you feel sick, right? So for virtual reality to be effective, you have to have this update come quickly. So the need for timeliness is really an application-specific thing. Okay, so people are aware of these applications. It's everyone maybe is familiar with some or all of these, and it's had some impact on network design. If you read about, for instance, the 5G cellular standard, one part of that standard is designed to reshape the protocols for allocating communication resources to make kind of messages have to support kind of low latency messaging, like 5 milliseconds or a few milliseconds delay. So in wireless access, people are working on this. In the fiber optic core, you can say, well, that core network, those packets are traveling very fast. But in fact, sometimes, right, if that cloud server, this picture it's drawn so that the person is on the left and the server's on the right. But in fact, usually the cloud server is over on the West Coast somewhere, and I'm on the East Coast. But the idea is the same. If the cloud server is somewhere across the country, there's 3,000 miles, and packets only travel at the speed of light, and the speed of light in fiber is actually less than in air, and the result is something like 20 milliseconds one-way propagation delay, 40 milliseconds round-trip delay. So somehow using a cloud server in a faraway place as the monitor is not going to work. Well, so networking people have a solution for that, and the solution is something they call edge cloud computing, and roughly the idea is that you'll bring these cloud servers everywhere, right? You'll bring a cloud server within 50 miles of wherever it is that people happen to be, and at the range of 50 miles, you can have 1 millisecond round-trip delays. So this is kind of the proposed solution among people who are interested in building systems like this. Okay, so now we have low latency 5G wireless access. We think about edge cloud computing, bringing the cloud close to you. And my contention in this talk is that isn't really quite enough, right? You still need to think about how to engineer the network for timeliness. The point I want to make in this talk is to say that timeliness is different and maybe somewhat surprising. So I've used this word timeliness, and to talk about it, you need a performance metric. And this brings me kind of to where this story usually starts. So I got interested with a WinLab graduate student at the time, Sanjit Kaul. He was a student of a colleague in the lab, Marco Grudister, who was going on sabbatical. And he said to me, I have an interesting problem to work on. And the problem was this V2V safety messaging. So So this is kind of a New Jersey Turnpike picture, and I guess you have similar things down on I-25 in Denver, but you have sort of a large ad hoc network, and each car would like to broadcast a safety vehicular status message to other cars nearby. And essentially the thought was you'd like these updates to be as frequent as possible, and as frequent as possible means you would like them to be timely in some way. So we were working on this problem, and we realized after some time that we were using a metric which involved a stochastic process that I didn't really understand. So roughly, you can think about this in the very simplest setting of the red car just talks to the blue car, and maybe in this V2V app, this cloud network thing is some kind of a wireless MAC protocol. And the red car is sending these timestamp updates to the blue car, and they have to go through this service facility. And what the blue car wants is the newest possible state information, the newest update. So the metric we were using was, how old is the current update at the blue car? What is the age of that update? Like, what is the difference between the time now and the timestamp of this most recent update? So this is a stochastic process, and it looks like this kind of a sawtooth waveform, and this is kind of the technical thing. If you start reading Age of Information papers, they all have this sawtooth waveform. So if I just explain to you where it comes from, all these papers will sort of become obvious. So it helps to point at things. So you start at some, there is a little red light. So you start at some time 0, and the current update the blue car has is some age. And as long as nothing happens, that thing, each second that passes, that update gets 1 second older. So the age grows at slope 1, right? It's every second it gets 1 second older. Then at some point in time, a new update is inserted by the red car into the system. And at that point, what happens to the age is nothing, because that update hasn't been received yet. So the update goes in, but until it's delivered, nothing happens. The age just keeps growing. So the age grows, and then at some later time, after some time capital T, this update is received. That's this down triangle symbol. And now the age drops, and everything here is with the geometry of sort of 45-degree right triangles. The age drops, and it drops exactly to the age of this update packet. Like the update was time-stamped here, and it aged capital T, and now the age is exactly the age of that update when it's received, the age of the monitor. And now you just do this over again. So this update was received, but now nothing is received, and the age grows. And something goes in, the next update goes in the network, and the age keeps growing, and when it's received, the age drops again. And essentially, this kind of sawtooth thing always happens because the age grows, and when an update is received, the age goes down to the age of that update. So this example is one where the update rate is kind of low, right? Like when the update goes in, it pretty quickly gets delivered, and when it does, the age really drops a lot. But the next update, you wait a long time for the next update to go into service, and while you're waiting for it to go into service and to be delivered, the age grows really tall, right? And this is bad, right? It's like you aren't utilizing your network resources sufficiently. You could make the age a lot smaller on average, this process, by sending updates more frequently. Okay. So if you think about then, well, let's really send these updates as frequently as possible. Let's generate kind of a steady stream of updates. So in this example, you send a red, a yellow, and a blue update in succession. The red update receives the service it received before. The age drops a lot, right? But the yellow update, it went into the system just after the red update, got stuck in a queue behind the red update, and it didn't go into service until the red update was finished. And then when it finally is delivered, the age doesn't drop very much because that update got stale. It got stale in the system. The system had congestion, and the result is the update that's delivered doesn't make the age go down very much. So this is kind of the opposite bad situation. Here the update rate is high. High update rates create congestion. Congestion makes updates go stale inside of the network. And that's also a system where the age at the receiver on the average is bad. Okay, so that got us to realize, oh, we don't understand this at all. Let's try to formulate a metric, and the simplest metric is just, well, what is the average value of this sawtooth process? So you look at the area under the sawtooth and you average it over time, and we know two things, that low update rate is bad because the age grows large, and high update rate is bad because the updates get stale. So both of those give high average age. There should be some sort of optimal way to send these updates. So when you decompose this average, you do some geometry on these kind of polygon areas, and you look at the inter-arrival time between two updates when they're generated, and the system time of an update, and you add up these areas, and you make some mild assumptions about ergodicity of the random process that a time average will converge, and you get a nice formula for the average age. So it depends on the inter-arrival time of updates, right, lambda. It depends on the second moment of these inter-arrival times, which is not surprising because it's an area calculation that depends on the area of this thing, which depends on y squared. And it also depends on a cross product term, correlation term between the inter-arrival time and the system time of that update. So T in this formula is an update that arrives at the system at time y after the previous one, then spends time t in the system, and that term is tricky. So it's tricky because there's correlation, and essentially the correlation is if the inter-arrival time is bigger, you wait longer to put in the next update. It gives the system a chance to empty out, and t will generally be smaller. So, but you have a nice formula, and then you can apply it. So we wrote papers that applied this to kind of all the elementary things we could think of, and I'll show you sort of what happens with the simplest elementary thing, which is MM1Q. So MM1Q, we replaced that complicated network, that whole cloud, with just a simple server. Packets arrive as a Poisson process. They have exponential independent service times. And what is the average age at the monitor for this very babyish simple system? As a difficulty of problem, it's something if you're teaching a graduate course in queuing, you can maybe make this be a take-home final exam problem, like and maybe half of the students will figure it out. There's a little bit of trickiness in the calculation. So you can find a nice formula for this, and the formula, when you plot it, looks like this, and it confirms kind of the intuition of what I sort of hand-waved and argued about, right? Which is at very low update rates, over here on the left side, the age is bad, and that's because the updates are received infrequently. And similarly, at very high update rates, the queue builds up, and once again, the age is bad, and as you get to approaching kind of the maximum load, the age will blow up. And so in fact, we see what we want to see. And then, of course, it says something else, that in fact, for this kind of very simple system, there's some optimal rate. that you should submit packets at. And if you're curious for the MM1Q, there's like a fifth order polynomial you have to find a zero of. And the answer is not a half, but 0.53 offered load is for some reason, the magic number that exactly balances leaving the system idle versus getting too congested. Okay, so this is like, oh, it's kind of a toy problem, and like, is this really, does it make a difference? And I contend it does, because it kind of offers a different view of delay than most people who work in networking in the way, from the way they think about it. So the traditional view of delay, however you choose to measure it, is that there'll be some kind of an offered load, and delay will simply increase with that offered load, with that update rate, right? And if you engineer for a system like this, you're like, oh, you can always have better throughput, right? But your your delay is worse and worse, right? And that kind of causes you to look at systems and say, oh, okay, I'll maybe put a constraint on the delay, and then that means I just limit myself to some maximum rate. Here we're really saying something different. We're saying, oh, in fact, whatever service facility you have, if you're interested in, and your system is a status updating system, you really should optimize your sending policy for the system, that it kind of has to be matched to it. And this example is for the MM1Q, but a variety of other queuing systems with first come, first served service and queue behave exactly the same way. Just the shape is the same, the numbers are different. So let's review here. I'll go back to standing where I'm supposed to stand. This age thing is an application layer end-to-end metric. And it's kind of nice because it doesn't require a network to understand application-specific performance measures. The hard thing about trying to figure out how to carry cyber-physical applications over networks is trying to figure out, well, does the network need to have some application-specific information? In general, if it does, for good performance, you have a problem because networks aren't really good at incorporating that. On the other hand, networks are good at managing timestamps. Maintaining timestamps and packets with timestamps and processing based on timestamps are very familiar ideas in networking. And then the next point is that age is not completely new. You get involved in something, you find this process you're interested in, and then if you dig around, you'll find out things that are very similar to age have been used in the 90s and earlier. For instance, Hector Garcia Molina worked on very similar age problems with respect to web caches in the 90s. So, and then the other point I want to make is that once you think, okay, I'm actually interested in building a system or having the network support these status updates, and my application really is better by optimizing the age, then it encourages you to think about redesigning the network. So over here, at low update rates, you can't do anything about this. There just aren't enough updates. But over here, it's really a fault of the network that there's this congestion that makes things stale. So when you think about this, you go, well, we had just some baby queue, and the staleness comes from, oh, the head of line update is getting the service, and these other guys are lining up behind it in this waiting room, and it's that stupid waiting room that's the problem. So maybe we should get rid of the waiting room. Right? Like get rid of the queue and the age will get better. So a queuing system that does this looks something like this. You serve the current packet in service, right? And you discard other stuff. So in this example, in fact, we can consider, for instance, doing preemption in service. You may be working on a packet, an update to transmit it, but if something newer comes in, you just abandon that and jump to the new thing, right? Just always work on the most recent timestamp update that you have. So this seems kind of like a stupid and maybe idealized mathematical model of a queuing system, but in fact, maybe many of you have seen this before because if you're part of Bachelor Nation, they use this queuing system all the time. So the Bachelor is here. This nice young lady is giving him a status update. And if you watch the show, right, here's what happens next. This happens every time. The next bachelorette comes over and says, "Can I steal him for a minute?" And she immediately, the first girl, for some reason, by protocol, is forced to get up and leave and hand over to this other girl who's going to give a newer update. I don't know why they do this, but in fact, I guess the Bachelor is really concerned about timeliness. Okay, so this is an important model. And when you analyze it, it's actually it's simpler to analyze because there's less memory in the system, and you get a new age curve which does something very nice. So as you load up the system, in fact, the age gets better and better. So that's a little bit specific to kind of exponential service, but not completely. So in fact, the lesson here in general is queuing is usually bad for updating systems. You don't really want to build systems that are busy working on old stuff when there's new stuff you can work on instead. So that's the message. It's kind of a simple one. Okay, so we worked on this problem in a variety of different ways, and one of the formulations we've thought about is the idea that, maybe there's a sensor, and the sensor is a network interface, and in maybe the very simplest setting, that network, that updates go through some facility that has some service time, that's some kind of a random variable, some random time it takes to deliver the update. The monitor, when it gets an update, sends, it's very hard to aim this over here. So the monitor then sends back an acknowledgement, and at that point the server knows, the system is idle, right? And then you might think that, okay, so this system, it's a state-dependent updating system. Like the network has some state. When it becomes idle, then you think about sending a new update. And there's no queuing in this system. Once the previous update is delivered, at that point, you can be like, at any moment, the sensor and the network interface is sufficiently integrated. You can just generate a fresh measurement and put in a fresh update into the system. And the question is, what's the optimal updating policy? Because I spent a few years of my life thinking that a just-in-time update is an optimal policy. So the just-in-time update is as soon as the other update is delivered, you don't want to leave the service facility idle because you're wasting resources. You immediately insert a new, fresh update. So it turns out this intuition that this just-in-time policy is optimal, it turned out to be wrong. I spent maybe a week of my life thinking I had an error in some program and some curve was wrong, but in fact, just-in-time updates are not optimal. The optimal policy is somewhat more complicated, and it involves keeping track of like the service time Y of the prior update. And in fact, the optimal thing to do is to be kind of lazy. If somehow like the system worked quickly and the prior service time was small, you should in fact wait. You should not put another update into the system. You should wait until at least some time that the gap between the timestamps of the updates is at least some parameter beta. and you optimize that on a per system basis. So, and the reason you do this becomes this minimum inter-update time. If somehow the service time is big, then in fact you immediately put in a new update. But if the previous service time is small, you wait, you be lazy. It's kind of like if your boss gives you a task and you finish it quickly, don't immediately volunteer for another task. You're like, oh, take advantage of having the previous thing. And so the reason is, I thought this was wrong at first, but the math said it was correct, and some MATLAB plots said it was correct. The intuition is as the prior service time goes to 0, if you immediately put another update in the system, that update will have almost the same timestamp as the one that was just delivered. So those two timestamps are almost the same, and the novelty afforded by delivering this next update, right, which you'll devote your system resources to delivering this update, which is almost the same timestamp as what went previously. So the message is that don't waste your network resources transmitting stuff that has very little novelty. That's what really comes out of the mathematics. And there was a trans IT paper that with some collaborators who are much better at math than I am, and they really kind of figured out kind of all of the details of this. That is quite interesting. All right, so we've also applied this to other problems, and I'll talk about a couple of these. First, we'll talk about replicated storage. So there are a lot of these systems that involve the source actually isn't just updating a monitor directly. It instead updates a collection of servers in the cloud, right? Because maybe many people are interested in this update and has to be stored in many cloud servers, so many clients in many places can see this update. And so this becomes a distributed database. If you kind of conceptualize it, kind of all of Amazon works this way. And so in these distributed databases, people have been interested in maintaining consistency. So roughly, it's the consistency means that the client gets the update that the source thinks he's going to get. And the way you can create this consistency is through a quorum mechanism. And a quorum mechanism involves the source sends the update to some or all of these servers, and some of the servers receive it quickly. And so in fact, there's here we have a write quorum of 2 servers that are the 2 that receive the message. And now the client wants this message, so he queries this collection of servers, and and in this case, I'll see how often I have to click. Yeah, there we go. So I'm not good with animation. My student did this for me, and it's a little too advanced for me. So so here we have a read quorum, right? Three servers are he has to read it from at least 3, and one of them has the update, and it works fine. So it guarantees if somehow the number that the write quorum plus the read quorum exceeds the number of servers in the network, then you're guaranteed to have the committed write delivered. Okay, so practice, it turns out that people sort of forfeit this strict consistency to make things faster. You can read newspaper articles that say Google says, oh, an extra half-second delay in delivering search results cuts traffic 20%. Amazon says 100 milliseconds of extra latency costs 1% in sales. I don't know if these things are real or fictitious, but people care. And so the technical question, though, is consistency good or bad for timeliness, right? Because in fact, like what was happening there was an update was being sent from the source to a collection of servers, and then this monitor client person was querying those servers for that update, and you'd like him to receive the latest possible update. Okay, So we did some analysis of this in the context of the Amazon Dynamo system. In this system, content is written to all the nodes, and the source continues this write and waits for it until he gets responses from W nodes that, oh, I've received this. That's the write form. And then the client tries to read from all the nodes, but he waits for the responses from the earliest R node. So this is like Dynamo-like, I think. So, you have consistency. You have, if W plus R is bigger than the number of servers. And the question is that a good idea? And when you do the analysis, and the analysis involves kind of order statistics of how long does it take for these updates to propagate to all of these different servers. In fact, for age-optimal quorum sizes, if you fix the size of the read quorum, the write quorum should be substantially less than the number of nodes. Like the intuition that Google says, oh, like strict consistency makes the system slow. In fact, strict consistency makes the updates that you deliver old. Right. So in fact, the intuition is there. So in fact, you can optimize this, and there's some paper you can read if you're really interested in the details. All right. So another problem we've worked on in this area is a problem in timely compression. This is kind of more of an information theoretic kind of a problem formulation. There's a source that generates symbols x1, x2. The symbols go through a lossless encoder that translates those into binary variable length code words. The variable length code words is, this is a binary data that then feeds essentially a radar binary, a bit pipe, right? And then the bits go through the bit pipe, and the decoder receives this bit string and has to see the code words and then reassemble the source sequence, the exit, right? So the way to think of this as an update is to think of each of these symbols xi as an update. And then the age of the system is you look at the receiver and you say, well, how many symbols behind is he in his decoding process? And you'd like to minimize that. And what you're doing here then is you want to devise the lossless encoder, right? Which in this case, with being a fixed to variable length encoder, you want to design and find the best collection of code words, right? A code for this source, right? That minimizes the age. So maybe the thing you're most familiar with if you take an introductory course in information theories, you want to do the best compression. So for instance, the best compression here is to do a Huffman code, right? But in fact, the Huffman code is not the optimal code for age. The Huffman code is the code that compresses the bits and uses the channel as little as possible, right? The code for age, when you work through the math, depends not just on the first moment of the code word length, it also depends on the second moment of the code word length, and you have to balance between those two things. And so in fact, there is a minimum age encoder, codebook, and encoder-decoder pair. And then when there's some second order questions, and they revolve around what should your block length be? And normally, like if you're doing compression, the bigger the block length, the better your compression. Here, the bigger the block length, your compression's better, but in fact, increasing the block length increases delay because you have to wait for an entire block to reach the encoder before you start encoding it, right? And when you look at these pieces, you reach the conclusion, which is it's kind of obvious afterwards, but in some way a little bit upsetting. And it's this, that as the rate of this channel increases, your communication resources are improving. And if you want to be age optimal, you really have to utilize those resources, and you compress less. So being age optimal isn't necessarily being efficient in terms of using the channel. You in fact compress less, use shorter block length, and that's actually better for age. The next kind of problem I'll talk about is one in caching dynamic content. So here we have a remote server, and he's maintaining these dynamic content items. You can think of them as maybe measurements of different physical locations or database records that are being updated by some external sources. And then over here at the other side of the network is a local cache that's maintaining copies of these objects for local people who are interested. This work was done with collaborators at Telecom Paris Tech who are interested in problems like this. And the problem here is that this red line through the cloud is some kind of maybe an expensive or slow link, right? So the question is, how do you utilize the resource of this slow pipe, and how do you decide which thing you're going to update, or in this simple setting, how do you decide what rates to use to update the different items? So in fact, there's a kind of a lovely answer, and the lovely answer is that these items have different popularities in the local cache. Right? Some items have many more requests, and so if you try to minimize a popularity weighted age metric over all of these items, what you want to do, as I guess the conclusion's been there a while, is you want to have the cache update rates for different items to be in proportion to the square roots of their popularities. And if you're a CS person, you say, oh, I think I've seen that before. The answer is yes. It was a similar conclusion by Cohen and Shankar about distributing content items over a CDN. Like different items have different popularity, and when you look for an item, you have to search nodes in the CDN to get to finding it, right? And they wanted to minimize the amount of searching that was going on. And in their case, the number of servers that should store an item should be in proportion to the square root of popularity, because these two problems, it turns out, are isomorphic. So you get kind of an answer that when you see it is actually familiar. Another problem we worked on was mobile edge cloud gaming, right? This is a little similar to augmented reality kind of situation. You have a game client, you're playing the game, you send client commands to some kind of a game server through the network. The game server integrates your instructions with the instructions of all the other players. And essentially, it's going to generate for you a stream of video frames, right, that represent your gameplay on your screen. And here, right, the question is, well, what should the frame rate be should the server use? And our belief is that, oh, this gameplay will be better if somehow the age of those frames is less, right? So conceptually, the way to think of this is that a received video frame is an update, right? And if somehow your frame rate is too high, sometimes you'll miss frames and you'll have to have a frozen frame event. The previous frame will continue to be displayed before you jump to the next. And that is then embedded in the age penalty. The age will grow because, in fact, you're looking at an old update, the frozen frame. And so we wrote a paper that kind of analyzed this for a simple system. And from it, you could see that, oh, there's an optimal frame rate. You don't want to send too fast. You create too many frozen frames. You don't want to send too slow because then the frames become old. And there's also an optimal display lag. Like this question of how long should this client, how much delay should he put in versus the generation of these frames in order to accommodate the network. And an age formulation lets you kind of analyze this. That was by my student Mernaz. Okay, so I think I'm getting here at the end. So there's this age of information performance metric. How long how old is the most recent update I have from you? This update I haven't made a point of saying this, it's suitable for comparing systems that are lossless with systems that are lossy. If you are a networking person and you think about performance analysis and you think about delay, generally you want to avoid comparing lossy and lossless systems. It's kind of like comparing apples and oranges. But under this metric, you can compare them, and if this metric really describes what your system cares about, lossy or lossless, the age is the age. What we learned, I hope, is that if you're trying to minimize this age, like you want to kind of match the updating in some way to what the system or network resources are. Like you can optimize this and find a minimum for the age. And possibly if you have control or you're able to design the system, you may want to re-engineer the system to try to not accidentally work on old stuff when there's new. And then the last thing is that once you start thinking about status updating, you can look at other kinds of problems and other cyber-physical system applications and either see that there's an obvious update or formulate an update, and maybe these tools could be useful. So if you're interested, some paper, this is this paper actually has appeared in Information Theory Transactions, and it's, and there's a couple other papers, they're pretty good. And if you are like, oh, I think I have a problem that could be updating, has anybody worked on this yet? There's like some community of, 50 people who have been doing this for a while. There's a collaborator of mine, Yin Sun at Auburn, who maintains a history of papers published in this area, and they're kind of nicely sorted by topic, and you can kind of quickly find out if any topic that you're interested in, whether someone has thought about in an age context at his website. I recommend it a lot. So thank you very much. I guess I'm done. Thank you. So, yes?
Your car example earlier, how do you synchronize the clock across the car receiving a message to other cars? How would it know if it's more recent? It's hard to synchronize the clock.
Yeah, I think there's work to be done in that area. So of course, like there are network synchronization protocols, right? And sometimes, for instance, a car is kind of a kind of a rich platform, right? So a car can have, for instance, GPS timing. It's using GPS. So a car maybe is an example where good clock information is available already. But I think there's a lot of problems particularly in sensor networks where the clocks are, if they have clocks, they're not reliable, right? And they run fast and slow, and there's too many to synchronize. And I think that's a very real issue. Like, how do you say, oh, this is newer than what came before? Can you rely on it? I mean, this is one of those problems I've been trying to get around. I mean, I'm trying to work on it, but so I think there's some very good problems there.
Well, I mean, it looks like there's all kinds of people already needing to rush to the next thing. So I think we'll end here. But before I let you go, we want to present to Professor Roy Yates a plaque in recognition of his distinguished lecture here. Let me read real quick from this. Presented to Roy Yates in appreciation for your Information Science and Technology Center ISTEC Distinguished Lecture, September 16, 2019.
Thank you very much.
All right, thank you all.